Today I'm going to show you how to convert from 3D into 2D. I came up with this idea just by staring at a box for like 2 days straight. Hopefully we're going to make something that looks like this. You can fly around and you can see that the two-dimensional perspective view changes as you move around. Here in this picture we can see that tangent of theta is equal to the ratio between y and x on this triangle, and then we're going to use that to relate the slope, because slope is rise over run. So if slope is equal to, we're going to call it m, then we can say that the green line y is equal to slope times your distance traveled in x. And here's a little diagram I made. This world is going to be a top-down view, so there's going to be a blue box just sitting out there in space, and your observer is your person that's just sitting down there at the very bottom of the screen right now. This red line on the left, which has a 0 on it, is going to be the left side of the computer screen, and then the right side of the computer screen, like the 1920th pixel, is going to be 100% of the way across the screen. So that's going to be this red line number 1. So you can either be 0 to 1 all the way from the left side to your right side of your computer screen. And now if we take that same equation we just figured out from that whole tangent of theta is equal to the slope and everything, and d, this yellow line, is related to the slope times half of this whole blue line of h. If this h is the total horizontal distance it takes up, at that distance away, then half of it is going to be like our x coordinate from the picture before. So in this picture, that blue x is like h divided by 2, and then the green y is like the d. And so now we can use this equation over here, this x prime or x projected, whatever you want to call it. It's equal to the fraction of x divided by h, and then you have this plus 0.5. That's just because we have this observer sitting right here in the middle. So if you had an x of 0 right here, so let's say the relative x position of this blue box right here is at 0, then it shouldn't actually be at 0, it should be at 0.5, so halfway between 0 and the 100%. That's why this plus 0.5 is on there. But this is just a simple ratio, just to show how you can get the projected x position along this little plane of existence right here. A ratio between this h value, and then you can figure it out from this whole distance away. And we're going to see how this distance is not just a distance in one dimension. We're going to be getting this coordinates for the x. We need to have this distance and the y and z directions combined together, just a Pythagorean identity. But yeah, let's start to code the program. Okay, first thing, we're going to be doing this in tkinter, just because we're going to keep it really simple. So let's bring in everything from tkinter. And then let's also bring in the math library, because we need to use that tangent function. Now let's set up the window. This is the same way that we made a window for the wave equation video, I'm pretty sure. All we do is start off with calling a tkinter window. Just open one up, name it, put a name of it, a cube. And then this is a new way I can just show you guys how to do. It's really stupid, but you can just put the string of a variable, like a number size. So this is going to be like a 1000 by like an x 1000 size screen. And then on top of this window, let's put a canvas, just put in a couple of parameters, and it should be good to go. We need to write a conversion function that can figure out this h value right here, solve for it basically. So move this equation around and just plug it straight into the above equation. So it's just x prime is equal to a bunch of stuff. So we just have one projected x value, not like two different equations. We don't need the two equations. It was just easier to use two equations to show what I'm trying to get at. So I'm going to name this function convert. We're going to need the coordinates of the vertex of whatever point we're trying to find in three-dimensional space. So if it has a coordinates of 5, 3, 7, we're going to need those, and it's going to be passed into the coordinates vector. Then we need our observer's position, so like wherever your character is flying around in, like dude that we were seeing in that picture before, wherever he's at in three-dimensional space. And then we're going to need a variable called size as well. I'm just going to have to call it the same thing as this 1000. It's going to be, our screen is going to be a 1000 by 1000. But if we want to have a different value for how far it is, like 1920 by 1080, then you need to put in two different sizes into this, or just hard code it straight into this function. That's probably the better way to do it, but I just want to show you guys a unique way to do it this time. So now we need this little x variable right here. Now if you guys remember, this is not just the x position in anywhere in space. If it's just like out in 1000, that's not just its x position, because your observer can also fly around, like you can move. So you need to subtract 1000 minus your current observer's position. There's only a difference of 100 there, so you need an account for that. This x is more of like an x relative. If we assume that the vectors for both the coordinates and observer are going to have just 3 components each, just x, y, and z, and x, y, and z, then we can just take x relative to be the 0th position of both of them. That means that the vectors we're pulling in are going to have like a form that looks like this. And now let's do the same thing for yr and zr. Okay, now we have all of the relative positions. Now we need to get the distance values. So this d right here is going to be different depending if we need the x position or y position along our plane. So if we're getting the x position along our projected plane, this distance is not only going to be the distance in z. If this is the z direction, like, you know, up and down on this screen, we also need the y direction. If you're like driving down a road and you were to look at something, you know, far away from you, like trees that are really often distance perpendicular to the road on the ground, then they're going to look really scrunched together. But also, if you look really far up in the sky, it would also have stuff that would be scrunched together, like a cloud in the sky gets really smushed together. So first we just want to get the x projected positions. Let's get distance and the y and z direction combined and use that for this d variable right here. So dyz is just going to be the Pythagorean formula, which is just the square root of 2 squares. We're also going to need to do the same thing for the y direction, so get the distance in the x and z directions combined. Sometimes we're going to get a return of like divide by 0. I'll show you why. So let's say that this h is going to be 0. Sometimes that can happen whenever this distance is also 0. Even if this cube is over here to the right of you and it's a distance in the yz direction of 0, it'll just destroy this whole equation and it'll blow up. It'll be a little bit clearer once to see whenever we actually plug in the full equation. So just start them off with 2000 because your screen is going to be, well, maybe not, but my screen is 1920 by 1080, so 2000 is going to be off the screen. You're not going to see it, so it's not really a problem right now. It would be a problem if we're connecting lines and everything, which we will be, but don't worry about it right now. So now let's go into the condition where dyz is greater than 0, which is basically all the time. It's rarely like 0. It can't be less than 0 because it's going to have this square root of squares. So it's basically always going to be greater than 0 unless if you're starting off your very initial condition. If you just load the screen in and your person's like sitting right on top of a point, it's going to shoot it off to infinity. So now let's combine those two equations I showed earlier. The relative x position times the tangent of theta. So I'm just going to put TOT for tangent of theta so we don't have to calculate it twice. So let's do that right here. Let's say that theta is 55 degrees. And then remember that Python does it in radians. So multiply by pi divided by 180. And then tangent of theta is equal to tangent of this theta. I'm just trying to, you know, spread everything out nice and evenly for you guys because it's your first time seeing a 3D to 2D conversion probably. Okay, so now we have this thing typed out. This is what I originally showed you. The problem is that in this diagram, I showed you this being 0 and 1, but in reality it's 0 to 100% of our screen. So well, all we need to do is multiply this out by our screen size. If this is, sometimes I would just do times 1920, you know, and then for the y times 1080. In this case, we just have a square screen, so we can just do times size, multiply that whole thing by its size, and then it should be all magnified perfectly. Otherwise, it would be going from 0 to 1 pixel and it wouldn't make any sense. Okay, just basically copy and paste it and change everything to be appropriate for the y conditions. Then type return xp, yp. All it outputs is 2 variables, your x and y position along whatever screen that you made. Okay, so we need the coordinates for a cube. 0, 0, 0, 1, you know, the whole combination of 8 points total. Here they are. Let's say the observer is going to be at 0, 0, -3, so pull them back a little bit out of there. Now we need to go through every element in this info variable we just made, take all the 3D coordinates, convert them in this function that we just created. And we're going to be doing this in a while loop over and over again forever just because I want to have the observer be able to move around. But then we have this for loop right here that's going to go through every single position in this info variable. Let's just call variable A and say is equal to convert function. And then the coordinates is going to be info of I, which is current position in this list, our current observer, which hasn't moved at all yet, and then the size of the screen. Okay, so now we can pull out the 2 projected values for x and y is going to be this A of 0 and y of 0. Let's use this function from tkinter called create_oval, which is kind of how you create circles. Let's say that oval equals 5. That's going to just give us a little thickness on these circles. So type in graph.create_oval. We're going to put our projected x's and y's minus oval, and then our projected x's and y's plus oval. So it's going to have like coordinates to make an oval. And I'm going to pick fill is equal to green. And now type in root.update and graph.delete all. Don't worry about the delete all right now, but just update the window and just run this script. There you go. You're going to get these. It's not the right number of points. 7's good because the x position and y positions are just going to be the same. Now come back up to the top and type in import keyboard. And from like my very second video I made, I showed you guys how to use the keyboard library just to detect if you have your finger on one of the buttons on your keyboard. Okay, so just copy this down. So say up here speed is equal to, I don't know, do like 0.005. What these are is the text pressing on 4 arrow keys, and then W and S move you forward and backward through the Z direction. The arrow keys are for the X and Y. So now let's create all the lines between the points so we can kind of see this cube a little better. The first thing that happens inside this loop is just creates a nothing vector. Now write the same for loop as last time, but put j as the index counter. Now use the thing we did in the wave equation video where we did graph.create_lines. Now we need to put some stuff into here, and I think a really good way to do it is to use this xp and yp that we already have up here. These are already created, so just say lines.append xp, yp. But we can't just do that. We have to put it in its own little vector itself. So now let's go through, create a line from every one of the y list to the j list, and then it's going to increment this I by 1, and then do it every single other point, including itself. So it's going to go from the very first point, make a line to all 7 other points, including itself, so 8, and then go to the next point and create lines, everything else in the cube, and then go to the next point wherever it's at. So all we need to do is say lines of I0, because 0 is the x projected. So now we have the x projected and the y projected, and then we can do lines of J0, then lines of J1 for the y, and then let's make a fill equal to red. So you can fly around with the arrow keys, and then the W and S go in. Something to keep in mind is that the coordinates are really weird with this, because in tkinter it counts x coordinates from the left side of the screen over, but it counts y from the top of the screen down. Our z is in and out of the page. It's hard to, like, whenever you start making graphs with x and y's and stuff, it just ends up being really weird because you have the y coming down. So usually it's nice to like put negative signs and stuff. It just makes it kind of a little bit of a hassle. But another thing is that right now we have nothing to control ourselves from going straight through this, and it just basically flips on the z. So there's a couple limitations of this very basic way to calculate it. All you can do is put some if statements in. You can also add in rotations to like take your observer and start rotating its head up and down like that. For now, thanks for watching. Hope you learned how to convert 3D to 2D. All right, bye.